Vector Algebra in 2 dimensions. Unit vectors. We usually describe vectors in terms of their components in a coordinate system like a Cartesian or rectangular XY coordinate system. Unit vectors have a magnitude of 1 and are in a well-defined direction. For instance, I hat in the positive x direction and j hat in the positive y direction. These unit vectors are the same no matter what point in space they're at. Vector addition. Let us now consider two arbitrary vectors, vector A and vector B. The outcome of adding vector A and vector B forms a new vector R that we will call resultant vector. Graphically, the resultant vector R is represented by drawing an arrow starting from the tail of vector A and ending at the head of vector B. Mathematically, the resultant vector is written as vector R equals vector A plus vector B. Also, we can add vectors A and B graphically with the use of a ruler to measure their magnitudes and a protractor to determine their directions. Here is a portion of Baguio City using Google Maps. If we started from the Lion's Head and went to Mines View observation deck, our displacement is represented by vector A. And then if we moved from Mines View observation deck to Tamawan Village, our displacement is represented by vector B. Afterwards, we have here vector C representing our displacement from Tamawan Village to Bencab Museum. The new vector starting from the tail of vector A to the head of vector C is the resultant vector R. Mathematically, the resultant vector R is equal to the vector sum of vectors A, B, and C. Here is another picture of Baguio City's map from the same app. If we will draw a coordinate system showing only the positive x and y axis, our origin is at Chaya. After a very good meal at Chaya, we are now ready to go to UP Baguio, where our displacement is represented by vector A. After our university visit, we decided to go to SM City Baguio for refreshments, where our displacement is represented here as vector B. Finally, we opted to go to Melvin Jones football ground to relax, and in the figure, our displacement is represented by vector C. Now, our resultant displacement is denoted by the vector R. We already know the resultant vector R is the vector sum of all the displacement vectors A, B, and C. In order to determine the magnitudes and directions of our vectors, we need the scale of our x and y axis as shown. We also need a protractor in order to find out the direction of our vectors. Components of a vector. We start by resolving the components of vector A. To find the x component A sub x, we project vector A down onto the x-axis by dropping a perpendicular from the head of vector A to the x-axis. The purple arrow is the x component of vector A. In the same manner, the y component a sub y may be determined by projecting vector A to the y-axis, and in this figure shown as the cyan arrow. The components of vector A can be resolved mathematically by noting that vector A and its components a sub x and a sub y constitute a right triangle where theta sub A is the angle from the positive x-axis to vector A. From trigonometry, the x component can be found by taking the cosine of angle theta sub A to be equal the adjacent over the hypotenuse, or cosine theta sub A equals a sub x divided by the magnitude of vector A. For the y component of vector A, sine theta sub A equals the opposite over hypotenuse, or sine theta sub A equals a sub y divided by the magnitude of vector A. At this point, I will leave this to you as an exercise. The scale used in this figure is not accurate, so there will be differences in your answers depending on your estimates. For vector B, the same process will be implemented in determining its components. As you can see in this figure, cosine theta sub B is equal to b sub x divided by the magnitude of vector B. Sine theta sub B is equal to b sub y divided by the magnitude of vector B. If we are to find the sum of vectors A and B, the new vector will be the resultant vector R as shown. Now, to determine the magnitude of vector R, we need to compute first its components, R sub x and R sub y. For R sub x, it is the sum of A sub x and B sub x. And for R sub y, it is the sum of A sub y and B sub y. Applying the Pythagorean theorem to determine the magnitude R gives the square root of the sum of squares of R sub x and R sub y. The direction theta R can be calculated using the equation tangent theta sub R equals R sub y divided by R sub x. If we go back to our original itinerary from Chaya, then to UP Baguio, then SM City Baguio, then to Melvin Jones Football Ground, our resultant vector R will have a different magnitude and direction. But first, we must determine the components of vector C by applying the same process we did before. Shown in the figure are the components of vector C and the angle theta sub C. Using trigonometry, it can be observed that the cosine theta sub C is equal to C sub x divided by the magnitude of vector C, while sine theta sub C is equal to C sub y divided by the magnitude of vector C. Now shown here is the computation of the magnitude of the resultant vector R and its direction theta sub R in polar form. Plane polar coordinates. Oftentimes, it is convenient to find a point in space by its plane polar coordinates r theta. The origin O and a reference line at theta equals 0 in this coordinate system is shown in this figure. A point in space is specified by a distance r from the origin to the point and an angle theta between the reference line, where theta is 0, and a line drawn from the origin to the point. As you can observe, the reference line is selected to be the positive x-axis of a Cartesian coordinate system. As a convention, the angle theta is positive when measured counterclockwise from the reference line and negative when measured clockwise. Negative of a vector. Now let us focus only on vectors A and B. If we take the negative of vector B, it will have the same magnitude but opposite direction as shown here. In this manner, we can now determine the process of vector subtraction. The subtraction of vector B from vector A is defined as vector A minus vector B equals vector A plus the negative vector B, resulting to a new vector R. Shown here is the comparison of vector addition and vector subtraction. Multiplication of a vector by a scalar. A vector A can be multiplied by a scalar C. Their product CA has the magnitude CA and a direction similar to that of vector A. The multiplication of a vector by a scalar C changes the magnitude of the vector by a factor C, but does not change the direction. However, if C is a negative scalar, the magnitude of the product CA is still CA, but the direction is opposite that of the vector A.